neutrons. What do? They go in and fission again. And then you have this chain reaction, and then it blows up and you have a nuclear bomb, right? Not exactly. We prevent that from happening by control rods that absorb our neutrons. Okay. In a reactor, there's two ways that we can make these beta negative emitters. Fission, we just talked about. The second way is neutron activation. And so what we're doing here, we're adding a neutron. It's the same neutrons. In fact, the neutrons come from fission. All right? And we're going to slow them down. And we're going to add a neutron. So neutron in, what comes out is a gamma ray. Okay? Which means my element doesn't change. You see that? The target and the product are the same element. The only thing that changes is this mass number goes up by 1. We can also make moly like this. And we do. We do. But the problem with making it like this, okay, when you make it through fission, you get different products. You get different elements. Different elements can be separated. These are the same element. And not all of this moly 98 is going to turn into moly 99. So we want moly 99, okay? But when we make it this way, we still have some moly 98 in there. This is called specific activity. This is the amount of radionuclide that you want divided by all the masses of the molys, okay? And so we get a low specific activity when we make it this way. That's why we like fission moly. Generators. See, I even put here, not really a production method. All right, the parent is made by a cyclotron or reactor. We put the parent in the generator, and then the generator just basically holds onto the parent until it decays. Inside of the generator, if you were to open it up and look on the inside, this whole thing here, this is the column. The column is only like an inch big. It's very small. And what's happening in here is the parent, the moly, is connected to the alumina. They form a chemical bond. As the parent decays to the daughter is not bound to alumina, so it falls to the bottom. And we're just going to run saline over it and collect the technetium. All right, a lot of different generators. So the ones that you should know for your board exam is the Molytech generator, the germanium 68 gallium 68 generator, and the strontium 82 rubidium generator. So there's several others. But one thing that you'll notice is in almost all these generators, the mass numbers are the same. So these are all isobaric transitions. Isobaric transition, remember, beta positive, beta negative electron capture. Shine decays to technetium. It does that 85 to 88% of the time, okay? Depending on what book you read. Some books say 85, some say 88. 12 to 15% of the time, it goes straight to Tech 99. Now, Tech 99 is not stable. There are no stable isotopes of technetium, none, okay? It's going to continue to decay until it reaches stability, and it's going to do that through isobaric transition, beta minus, until it reaches ruthenium. But look at this half-life, 2.11 times 10 to the 5th years. So that means that it's a very low yield beta negative emitter. All right, 3 tests that we do on the generator eluate. How do you keep these straight? It's very important to keep them straight. Radionuclide impurity, you're looking for a radionuclide that's there that shouldn't be there. So you're looking for moly in your tech. You're looking for strontium in your rubidium. Radiochemical, you're looking at the chemical bond. Chemical bond just means the sharing of electrons. So the chemical bond between the technetium and the ligand. So you're looking for free tech and hydrolyzed reduced tech. And then chemical impurity, that's just the alumina. With radionuclidic impurity test, we're looking to see if there's moly in your technetium. Now, if you're studying from any old Borg material, here's what happened. All right, this was required after every elution for a really long time. And then the NRC was like, you know what? It really doesn't fail after the first solution, so let's just change it so it's only after the first solution. Like, okay, that's great. And then they changed their minds back. They're like, no, we've actually have some evidence that it does fail after the first elution, so we need to change it back. But there's some old study materials out there that still say you only check it after the first solution. That's not the correct answer. You have to check it after every elution. That is the correct answer. And how do you do this? We're going to take advantage of the energy of moly being high energy and the energy of technetium being low energy. And we know that with shielding, if it's higher energy, we need more shielding. So we're going to put our vial in the moly shield, put the cap on it, put it in the dose calibrator. The moly shield's going to block the technetium and tell us how much moly there is. And we take it out of the moly shield and it tells us how much technetium. We keep it in microcuries of moly per millicurie of tech. This is the limit. It expires in 12 hours. All right, we're going to skip through that because we don't have time. All right, radiochemical impurity testing. This is your thin layer chromatography. You know, you guys are actually lucky. Well, maybe not. It depends on who you program your trans. Maybe you're unlucky. But when I was in school, we had to know which type of paper, the silica gel or the other one. See, I don't even remember what it is. We had to know which solvent was used. We had to memorize every single limit for all of those. Maybe your program director makes you do that, but you really don't need to know that anymore. You do need to know what radiochemical purity testing is. It's a good idea to know that the two solvents are acetone and saline, but you don't need to know which go with which anymore, okay? You need to know that these are the two forms that are not desirable. You don't want hydrolyzed reduced or free tech. And you need to know how this is done. So you put the drop on your paper, the solvent moves up. Where the solvent ends, it's called the solvent front. We're going to cut it in half because the two parts are going to separate, and then we're going to calculate what our radiochemical impurity or purity is. As a rule of thumb, free tech is at the top. You can think of this as it's free to fly away. Hydrolyzed reduce, it's heavy. Begins with an H. Heavy stays at the bottom. All right. And then the last one is chemical purity testing. The only chemical we're looking for is alumina. 10 micrograms per ml. And don't just memorize the 10 because on your board exam it could say 10 in every answer and they might change the units. So make sure you memorize the units as well. Now this is what we call a colorimetric test. This paper is made of this type of acid, and the kit comes with a standard, right? The standard is going to have 10 micrograms per ml of alumina in it. And you're going to put a sample of the standard on your acid paper, and it's going to turn pink. It's going to make the pink pinker. I don't think pinker is a word. It's going to make it more pink, okay? And then you're going to put your drop. It's kind of hard to see, but there's a drop of our eluate there. And we're going to compare to see if that drop turned the same pink color. And if it did, then it fails. All right, theoretically, we talked about last time. We're not going to talk about that this time. So we're going to move on. And our last topic, 15 minutes left. You can do it. 15 minutes left. This is a long day. Radiation safety, okay, before our Kahoot came. And I know some of you joined in the Kahoot last time. I see Nicole and Haley, you guys are part of the Kahoot. I think your class swept first, second, and third. That was a pretty impressive showing. Of course, there were more people in your class, but we're not going to go there. But the Kahoot game's going to be fun. Okay, but we can't do Kahoot until we do radiation safety. So, the regulations. Make sure you know 19, 20, and 35. Those are the three you need to know. I doubt you'll get a question about 19. If you do, it's probably going to be notice to employees or inspections. 20 and 35 are the big ones. If your question is about radiation protection, it's 20. If it's about licensing, it's 35. Okay, that's what you need to know. Know your signs. Radiation safety education. This is where most of the NRC violations come from, is lack of radiation safety education. And the reason isn't because you don't get radiation safety education, it's because it's not specific to your license. So you know how every year you have to do fire safety, and you have to do the HIPAA, and you have to do, the computer safety, all that kind of stuff. You're also supposed to do radiation safety training, and it should be specific to your license. What do I mean? How do you check in a package in your department? How do you take care of a radiation spill? It should be specific to what you do. Who gets it? Anybody over 100 millirem. That 100 millirem is an important number because that is what differentiates the public from not being public. Okay, we'll talk a little bit more about that. All right, restricted area versus unrestricted area. If it's an unrestricted area, that means there's no signs, there's no anything. Anybody can go in those areas. Waiting rooms are unrestricted areas. We have to ensure that nobody gets more than 2 millirem in any hour or 100 millirem in any year. Okay? Now, this isn't 2 MR per hour. This is total 2 millirem in 1 hour. And the way that we do that is we evaluate, where a hot lab is. We're going to check on the other side of the wall, and we're going to see how much radiation is in that hallway. And then we're going to use an occupancy factor. How much time would somebody spend there? And then we're going to do one of those time calculations. Now, this doesn't include contributions from patients. So we can inject 30 millicuries of cestamibia into a patient and send them back to the waiting room, and we don't count that. But if we take a syringe of 30 millicuries of cestamibia and put that in the waiting room, then we're going to get in trouble. It doesn't make sense, but that's the rules. Now, restricted areas, you can have more than 2 millirem, and you know how you make it restricted? You post a sign. You just post a sign. All right, leak testing. Leak testing, this is a glorified wipe test. That's all it is. We're just doing a wipe test on our sealed sources. Do it every 6 months. And I hate that the limit is 0.005 microcuries. It's like, well, wait a minute. When I count something in well counter, I get counts per minute. I can convert that to DPMs, but why is this in microcuries? Well, you can convert it because we know how to do that, right? But on your exam, it's going to say 0.005 microcuries. That does convert to 11,000. Oh, no. Get it right, Sybil. 11,100 DPM. All right, at the same time, you have to do a sealed source inventory. And if you've ever worked in retail, you understand this, right? If you worked at TJ Maxx, what do? You go in, you're like, okay, it's inventory time. What do I have? How many do I have? And where are they? You're gonna do the same thing. What do you have? I've got a cobalt sheet source. Where is it? It's in the lead line casing in the closet. How much do I have? I have 5 millicuries. All right, those are the 3 things you have to document, sign and date. All right, waste disposal. A lot of different ways we can do this. Decay and storage. If you decay something in storage, the half-life has to be less than 120 days. I kid you not, I went into a department because when I was a program director, I was also a clinical coordinator, so I'd visit my students in the clinic. I went into this department. They had 3 cobalt 57 sheet sources in their closet. And I'm like, what are you doing? Those are cobalt. They're like, yeah, we're decaying them in storage. I'm like, half-life is 271 days. You can't do that. See what they said? They said, well, do you want one? I was like, none of this works like this. You can't give me your cobalt sheet source, okay? And you can't decay it in storage. This is a huge NRC violation. You have to send it back. So 120 days. Now, when you do decay something in storage that's less than 120-day half-life, you keep it until background. This 10 half-life thing is no more. That's old rules, okay? I'm talking before 2002. Keep it till it's at background. Okay. Now, if you transfer it to an authorized recipient, which is what you do with your cobalt sheet sources, you're going to transfer that. You have to pay for it, okay? And it can cost a lot of money. You can also do sewer discharge. We used to do that. If our dose was too hot, just squirt a little bit in the sink, run the water, contaminate your hot lab. We did. You can still do that if you want to, but you have to do this wastewater discharge rate thing, and nobody does that calculation, and so it's not a good idea to do that. And then also release in the atmosphere, like I told you about the xenon, the bag of xenon. All right, surveys and wipes. How often do we have to do them? Everybody says daily surveys, weekly wipes. Nope. Reasonable schedule. Okay, whatever's in your radioactive materials license is how often you have to do wipes and surveys. And you know, people think that we do these to find contamination and clean it up. We don't. We do these to monitor our practice. So if Sarah and I are working together, okay, and we do surveys, you know, maybe we do them every day. And every day we find that this particular corner of the room is hot. We're going to look at what's going on in this corner of the room. Not like, well, that's where Sarah injects all her patients. Obviously, she's pretty messy, okay? So we're monitoring practice in order to change our practice so we don't contaminate. That's why we're doing wipes and surveys. 10% rule, this is where we do wipes and surveys. Wherever anybody is likely to receive 10% of the annual amount. Hands and feet, why do I have this on here? Because before you leave your department, even to walk down the hall and get a patient, you're monitoring your hands and feet, right? No, you're not. But on your board exam, you are. And when the NRC or the state comes in to inspect you, you're monitoring your hands and feet before you leave the department. All right, minor spills versus major spills. The NRC doesn't actually have a list that says, oh, these are minor spills and these are major. A good rule of thumb, if it's diagnostic over 100 millicuries, that's major. If it's a therapy, that's major. Otherwise, it's a minor, okay? Now, what you do is common sense, okay? So you can memorize all this stuff, or you can just think common sense, okay? If Sarah and I are working together and I injected a patient and I spilled a drop of technetium on the table, this is a minor spill, what am I gonna do? I'm gonna say, hey, Sarah, I just dropped some technetium here. I'm gonna notify people in the area. Then I'm going to prevent the spread and put some gauze down on it, probably so I don't lose where it is. I'm going to clean it up. I'm going to survey the area. I'm going to check around, see if I spilled somewhere else. I'm going to check myself for contamination, and then I'm going to report this to the RSO. Right? We report all of them to the RSO. No, we don't. We don't. But on your board exam, you do. Okay? On your board exam, you do. Major spill. I just dropped 200 millicuries of Lutathera.
40% of the NMTCB exam is clinical
Everybody out.
procedures. We're going to spend some time there. Followed
Prevent
by
the spill, shield it, close and lock the door, get the
and then we're
RSO
going to get into physics,
We
instrumentation,
talked about
radiopharmacy,
required postings yesterday.
etc.,
So let's go through
etc.
that.
And we're going to end with the Kahoot. So let's jump into
Alright.
Math Mania.
Types of packages.
Get your
Type
calculator
A,
warmed
Type
up. We're going
B,
to start with
accepted
effective
package.
half-life. So
Type A, this is what our doses come in. 7A, that refers to the card. It says type A right on it. These are type B packages. You're not going to see any of these. Okay, so this is way more shielding than what we possibly need. There is this rule about shielding alpha emitters in a type B package, which make sense. I don't understand. I mean, because you can shield an alpha emitter, you know, in your hand with a piece of paper. Why would you need to put an alpha emitter in something like this? Hopefully that doesn't happen, because each one of these packages are about $100,000. All right, accepted packages. This is when we send our material back. What do you need to know about this? A lot. You need to know that an accepted package is also called a UN 2910, and accepted packages have to be limited quantity, which is different than an exempt quantity. All right, sometimes you hear these terms like, what does that mean? An exempt quantity is a quantity exempt from the regulations. That means you can have 10 microcuries of cesium-137 if you want. There's a list of exempt quantities in the NRC regulations, And for each radionuclide, it basically says how much you can have without a radioactive materials license. So if you want to go buy 10 microcuries of cesium-137, you can do that. I don't know why you would want to, but you can do that. That's an exempt quantity. A limited quantity is the amount that can go in an accepted package. And you know, the reason we send these back in accepted packages and not type A packages is because our departments aren't licensed to ship radioactive material. The radiopharmacy is licensed to ship radioactive material, but we're not. So this actually happened one time. On campus, a box was delivered to a hospital. This was on the academic institution I was working at. A box was delivered to one of the hospitals, but it was the wrong package. It was the wrong hospital. That package was supposed to go to a different hospital, also on campus, okay? And so the question was, how can we, the hospital that got the package, get this package to the other hospital? Because at that point, it's a type A package, and we're not licensed to ship type A packages. So we went to our RSO and like, what are we going to do? Should we call the radiopharmacy to come back and get the package and deliver it to the other hospital? And normally the answer would be yes, okay? But since it was on our campus, we were able to walk it over there. But if it wasn't on our campus, we would have had to have the radiopharmacy come back, pick up that package, and even though the hospital is literally right next door, they would have to transfer it because we cannot ship type A packages. We have to turn them in to accepted packages. All right, make sure you know your labels. I'm sure your program has given you all that information. All right, where's my limited quantity slide? All right, I talked about limited quantities, and we're not going to talk about it. All right, how is our exposure measured? Deep dose, committed dose. Both of these are internal organs, okay? How much we're being exposed to internally. Deep dose is from external sources, committed dose is from internal sources. This means, committed means that you inhaled, ingested, or absorbed radioactive material, right? Why would that happen? Well, your coworker doesn't like you and squirted some technetium in your coffee this morning. Hopefully that does not happen. So at one time when I was a student, the technologists were playing around, and one of the technologists had a syringe of saline, and another technologist came in and he acted like he accidentally squirted the saline on another technologist, but he said it was technetium. And I mean, that tech freaked out because thought he was contaminated with technetium. That is a very bad thing to do, okay? Don't ever do that. But if you get that dose inside of you, then that is a committed dose. You add these two together, that's your total effective dose equivalent. That is what your TEDE, that is what you're going to have on your badge report. The shallow dose, that's from your extremity badge, so your ring badge, or it can be extrapolated from your whole body badge. Lens of the eye dose, they actually have badges you wear on your eyeglasses. And so the lens of the eye dose, or that can also be extrapolated from your whole body badge. Make sure you memorize these. Easy way to memorize these, the public dose is 100. These are all special members of the public, and they all get 500 milligram. All right, we're going to end with just a little bit of radiation biology. I'm going to talk about linear energy transfer. You know, don't memorize these things. Understand what they mean. All right, linear means line. Energy, KeV. Okay, lines are measured by distance. Micrometers, civil. KeV per micrometer. There we go. Now I get it right. How much energy is deposited per distance, linear energy transfer. High LET is alpha, low LET is everything else. This is what it looks like. As alpha particles move through space, they go straight. These are all ionization events, a lot of ionization events in a short period. Low LET, not many ionization events, and also no that it travels in an erratic pattern. All right, which takes us to here. Non-stochastic versus stochastic. Non-stochastic is also deterministic. The dose determines the effect. We know how much dose is going to turn your skin red. We know how much dose is going to cause your hair to fall out. We know how much dose is going to cause acute radiation syndrome. Stochastic is probabilistic. The dose increases the probability. Increases the probability you're going to have cancer. If you increase the dose, it's not going to make your cancer worse. It's just going to increase the probability that you're going to get it. That is what ELERA is based on, and that is what the linear no threshold model is based on. All right, early effects. I'm not going to go through this. Hematopoietic is the first one that you are affected by. And I will tell you one last story about cataracts. Okay, so cataracts is a non-stochastic or a deterministic effect. It is real, okay? You expose to enough radiation, you're going to get cataracts. Now, there's a reason why all Gen Xers are getting cataract surgery right now. And the reason is we sat too close to the TV. Our parents warned us. They did. The old TVs, you know, the really big, thick ones, they have cathode ray tubes in them, meaning they are producing x-rays. And our parents would always tell us, I don't know if your parents told you this, but they were like, don't sit so close to the TV, you'll go blind. Well, they were right, because we all have cataracts now, okay? Now, the new TVs don't have cathode ray tubes in them anymore, so we don't have to worry about that. But that is something that you want to, you know, pay attention to is cataract formation. All right, that is it, my friends. We did it. Whoops. Okay, so we're going to take a break, but what I'm going to do is I'm going to bring up the Kahoot screen, okay? And for those of you that have not played Kahoot before, let me stop sharing here. I'm going to explain this real quick before you leave. So, post live. This one. Click. Are you hearing the music or can you hear me?
We can hear both.
You can hear both. Okay, good. All right, so you will scan the QR code. And when you scan the QR code, it will ask you to put in your name. Again, feel free to use a creative name. Keep it clean though, okay? The dirtiest name I accept is hot trash, okay? So keep it clean. Haley's, that's the other Haley, is putting in SNL, Gus, Tim, all right. Oh, you are bravely putting in your own names. At the end, what we'll do is whoever finishes first, second, and third, you'll email me and let me know that that was your name. And then I will send you your gift card. So we're going to take a break. We have 13 minutes. Get ready, because this is going to be a lot of fun. And I'll see you in 13 minutes.